Yo, what is up guys? So today I want to bring you guys a video about QuickSort. So QuickSort is one of the most widely used sorting algorithms out there for sorting arrays, and it has a time complexity in the best and average case of n log of n, and worst case scenario n squared, so the same as the previously presented algorithms in the channel, so bubble sort, insertion sort, and selection sort. But on the best and average case, it's a lot better. And when it comes to space complexity, you can consider it constant if you're not considering the recursive stack space. But as this is a recursive algorithm, and in reality we're using the recursive stack space, it's fair to assume that it has some space complexity, and in the worst case will be O of n. And I'll showcase how the algorithm works here, but I'll briefly explain what we're going to do. So we're going to recursively call the algorithm, meaning that the algorithm is defined in terms of itself, so it's a function that calls itself at some point, and at some point we have a break statement that will return the stack call back to the initial function call, and we'll have the algorithm sorted. So we have a setup here, so this is the array we're going to sort, and we have two pointers down here, the pink pointer and the yellow pointer. The pink pointer will iterate through the array on the current iteration, and the yellow pointer will count how many elements we have smaller or greater than the pivot, and the pivot will be an element we define within the array that we will be using to compare the numbers to the pivot. So the algorithm works by using a list theory, where it states that if you have a sorted list or a sorted array, if you pick any element within that array, all the elements to the right are going to be smaller or greater than, and all the elements to the left will be smaller or greater than, depending on the order of the sorting. So to standardize things here, I'm gonna say that we're always gonna sort in ascending order. So if you pick a sorted array, and you pick one element within that sorted array, as it is in ascending order, every element to the left will be smaller or equal to the element you've picked, and all elements to the right will be greater than or equal to the element you've picked. So we'll use this concept here to partition this array. So we'll create a function called partitioning, where we'll try to isolate all elements that are smaller than the pivot on the left and greater than the pivot to the right. And to do so, you have to choose a pivot. For simplicity sake, we'll select the pivot being the last element. It's also easy to implement with the pivot being the first element, but you could choose any element within the array. It's just gonna make your life a little bit harder to implement the algorithm correctly if you choose, for example, any of the elements in between the array. But for sake of simplicity, we're gonna choose the pivot being the last element in the array. And what we have to do now is iterate to the array and ask the question: the pink pointer is pointing to an element, so is the element pointed by the pink pointer smaller than the pivot? No. If not, we're just going to increment the pink pointer. So we're going to increment the pink pointer. Now, is the element pointed by the pink pointer smaller than the pivot? In this case, yes, 3 is smaller than 4. So on top of incrementing the pink pointer, we have to swap the current pink pointer with the previous yellow pointer, because this will ensure that all elements that are smaller are getting thrown to the left, and all elements that are bigger are getting pushed to the right. And after we swap 3 and 8, in this case the pink with the yellow, we're gonna increment pink and increment yellow, because now we have found an element that is smaller. That's why we increment yellow. Yellow is the counter of smaller elements than the pivot, and we keep doing this. So is 1 smaller than 4? Yes. So we're gonna swap the pink with the yellow. So swap 1 and 8 and increase the pink and the yellow. Is 0 smaller than 4? Yes, it is. So we're gonna swap the pink and the yellow. So swap 0 and 8 in this case, and increment the pink and the yellow. And once we reach the end, meaning that the pink pointer is pointing to the same index as the pivot, we'll stop the algorithm, and the last thing we have to do is swap the pivot with the yellow pointer. If we do so, we'll get this behavior, and now we have the whole array where we have the pivot pointing to an index where all elements to the left are smaller than the pivot and all elements to the right are greater than the pivot, and we have to recursively call it on the subarrays to the left of the pivot and to the right of the pivot. So in order to do so, let's do this partitioning algorithm on the subarray 3, 1, 0 on the left. Now 0 will become the new pivot, as it is the last element of the subarray. We compare 3 with 0. Is 3 less than 0? No, so we just increment the pink pointer. Is 1 less than 0? No, so we just increment the pink pointer. And we have reached the point where the pink pointer is pointing to the same index as the pivot. We just swap the pivot with the yellow pointer. And now our new pivot position is somewhere where all elements to the left are smaller and all elements to the right are greater. As we don't have any elements to the left, that's obviously why 0 here is the smallest element in the subarray. Now we just have to call recursively in the subarray 1 and 3. Now 3 is the new pivot, as it is the last element in this subarray. And we have to ask the question, is 1 smaller than 3? Yes, it is. And now we're going to swap the pink with the yellow and increment both. But in this case, you could either ignore the swap because the pink and the yellow are the same position, so you're swapping the element with itself. And once we increment, we're going to have the pink now pointing to the last element, or to the pivot index, and now we just have to stop the algorithm and swap the pivot with the yellow pointer. And again, as they are pointed to the same index, you're going to swap the element with itself, and you can either ignore the swap or swap it with itself and recursively call the partitioning on the left and right subarrays. Now we don't have any right subarray because 3 is the biggest element within this subarray, and we have only the left subarray containing only one number. And of course, if you have only one number, there is no need to compare anything because it is already sorted. So we just have to return this element. Okay, so we just return number 1, and once we return it, we have the previous sorted subarray 1 and 3. We return this because it's already sorted. We have 0, 1, and 3, and this is already sorted. We return it to the first original array, and now we have the right or the left subarray completely sorted out. So 0, 1, and 3, and the pivot, the original pivot is in its correct position. And now we just have to recursively call on the right subarray, and to do so, the right subarray is only one number. If it was more numbers, if it had more numbers, we would apply the same strategy as we applied on the left subarray. But as it has only one number, we're just going to return number 8. And once we return it, we have the array fully sorted. So 0, 1, 3, and 4. And that's basically how you implement how QuickSort works under the hood. So this is the algorithm we're going to implement in code. So now we're going to hop onto the coding implementation of QuickSort. So let's now hop onto the file. So I've created a file called quicksort.c that we'll be using here. So what I want to start with is including our standard input-output. So this will provide us a functionality for printing. And in here, I want to create a macro. So let's define a macro here called nElement. This will help us out calculating the number of elements within a given array. So the way we do this is we pass in size of the array and size of divided by the size of the array first element. So what we're essentially doing here is we're getting the size of the array in bytes and dividing by the size of the first element of the array in bytes, and this will give us the number of elements within the given array. So let's create the main function. Let's return 0 if everything goes as expected. And now I want to define the arrays we want to test the function or the sorting algorithm on, and I also want to print them so we can visualize them before and after the sorting algorithm has been applied to them. So first, let's create a print statement that says arrays or original arrays, and let's create here an array of integers. First one will be 8, 3, 1, 0, and 4. I guess this is the same one we used in the presentation. Array number 2, this will be 12, 17, 8, 2, 4, 9, minus 1, minus 2, 0, and 19. So let's use a bunch of numbers here, and let's repeat a number somewhere. Let's repeat number 12 for some reason. And let's create a third array, and this third array I want to keep it already sorted. So this will be 45, 46, and 47. And a fourth array that will have only one element inside it. So this will be 337. And we have to print the arrays so we can easily visualize what's happening. So here I pass the array and the size of the array. So this will be an element of the array from the macro we've established before, and paste it 3 times. And now let's insert here number 4, 3, 2, and here the same thing, 2, 3, 4. And let's define the print function here, void print array. And in here we're gonna get as an argument an array and an integer called size. And I want to first start off printing only a opening bracket like this, so we can print this array in a formatted way. And in here I want to create a for loop with int I equals 0. I will be less than size minus 1, so we're going to the second to last element in the array because I want to print the last element in the array in a separate line. And in here let's print the elements in this following format. So the number followed by a comma, or followed by the comma and a space. And in here I want to print the element array of I, and last but not least I want to print the last element in its own line. This will be the number followed by a closing bracket and a break line, and in here the array of size -1. So this will be the last element, and all it's left to do is create a function declaration, and we can compile it and run, see if there are any errors. So GCC QuickSort output QuickSort, no errors. So let's execute it and test it. So printing function seems fine. So these are the arrays we've established within the code, and here they are printed in their original state. So let's hop back onto the file and quicksort.c, and from here we will implement our sorting algorithm now. Now let's create the quicksort function. In order to do so, let's create a function called quicksort that will receive the array we want to sort, and we'll receive two arguments. I'll call them start and end. And in order for us to do that, I'm just writing this in order for you to understand. But this will be the starting index of the array. So every array starts at index 0, and the ending index of the array. And this index is number of elements in the array. Number of element in the array -1, because the number of elements is the index, last index plus 1. So if we get the number of elements -1, we get the last index. We have to copy and paste it 3 times because we have 4 arrays we want to test this on. So this is array number 1, 2, and 3. Oh, sorry, 2, 3, and 4. And in here, 4, 3, and 2. And once we finish creating the quicksort function, we also want to print the sorted arrays. So let's create a printf statement here called sorted arrays, and let's add a break line here at the start as well, just to make things easier to visualize. And in quicksort here, we have to copy and paste these printing functions here. So now we're printing the original arrays, we sort them, and we print the arrays already sorted. So let's move on to the implementation of the quicksort function. So let's create here a void quicksort. So let me just open the presentation here real quick. So if you take a look here at the presentation, we'll essentially perform this first iteration called partitioning every time we call the quicksort function, and this partitioning will return us the index of the pivot. So the partitioning is these comparisons here. So we compare the pink pointer with the pivot, and we keep doing that until we reach the end. And once we reach the end, we'll switch the pivot with the yellow pointer, right? So that's why we're switching the pivot here with the yellow pointer. And now the pivot will be in a different position, and the new pivot position will be the index of the yellow pointer, right? So this will be the return of our partitioning function. And once we get that, we will use this to perform the quicksort function again into the left subarray and into the right subarray. And in order for us to do so, we'll get the start on the left subarray will be 0 as always, because it always starts at 0, and the end of the right subarray will be the new position of the pivot -1. So it will be pivot -1. So we'll go from start being 0 and end being pivot -1. And on the right subarray, we'll start at pivot, the new pivot +1, and we'll go up to the original end. In this case, we'll only have one element, and so in this case, the pivot, the pivot +1 and the end of the array will coincide to be the same element, and in this case, we'll just return. So let's implement the function here. Let's go back to the code. So quicksort here will be receiving the array, so integer array will receive a integer start and an integer end. And in here, for the sake of making things easy to understand, we will only run the quicksort function if the end is greater than the start, because the end represents the last index of the subarray or the array, and start represents the starting index. If start is equal to end, we only have one element, so we do not have to call this function, we just return, right? And if end is greater than start, we have at least 2 elements, and then we have to call partitioning. So let's call partitioning on the array, and we'll pass in the start, and we'll pass in the end. So the end will be our pivot. So in order for us to actually use the pivot concept we are using here in the presentation, I will just create a placeholder variable called pivot, and this will be equal to end, just so we can use the pivot keyword here. So instead of end, we'll pass in pivot to the partitioning, and this partitioning function will return the index of the pivot after the array has been partitioned So we can use this index here. So let's say that pivot will be equal to the return of partitioning. So we'll have this index, and we'll now perform the quicksort function again on the left and on the right. So let's call quicksort on the same array, but now the start on the left, so this will be the left, right? So the start on the left will be 0, and the end on the left will be the pivot minus 1. So this will be the pivot minus 1. And now let's call quicksort on the right subarray. So it will be the same array. The start of the right subarray is the pivot, the new pivot, plus 1. So this will be the pivot plus 1. And the end of this right subarray will be the original end. So that's why we're passing end here, okay? So this is essentially what we have to do in the quicksort function. This is all we have to do in the quicksort function. Now, the algorithm itself, the most important part of the algorithm is actually the partitioning function. So let's implement the partitioning function here. So this will be an integer because we will return an integer. So partitioning. This will receive an integer array, an integer start. Oh, what? An integer start and an integer pivot. So we can use the concept of pivot. But if you look at here, the pivot will be the last index or the end. That's all we're doing here, okay? So this is all we're doing. We're just creating the new variable called pivot to placeholder the end variable here so we can use the concept of pivot. So in this case, what we have to do in the partitioning is, if you look back here at the first, we'll have a pink pointer and a yellow pointer, right? So the pink pointer will be represented by the letter J, and it starts not at 0, because if we start at 0, we're passing the whole array. We're always going to start at the 0th index. We don't want that. We want to start at the start variable we've passed in this function. And the same thing applies to the I variable that will represent us the yellow pointer here. So the yellow pointer will also start at the start, okay? So we have set our pink pointer, we have set our yellow pointer, and we have set our pivot by the argument in the function. So what we have to do now is loop through all the items in the array or in the subarray until the pink pointer reaches the pivot. So while the j is less than the pivot, meaning that our pink pointer has not reached the pivot yet, we will ask the question if the element in the array pointed by the pink pointer is smaller than the pivot pointer. So it's smaller than the pivot pointer. If the element pointed by the pink pointer is smaller than the pivot pointer, we will increment the pink pointer by 1, increment the yellow pointer by 1. But before that, as we see here, so we will have to swap these two elements, because let's get this case here. So if 3, in this case, is smaller than 4, we have to swap the pink pointer with the yellow pointer, because the yellow pointer is the counter of how many elements smaller than the pivot we found. And at the start this will be 0, so, or at the start this will be start, and we'll swap the first smallest element with the counter. So let's swap in the array the position of our pink pointer and our yellow pointer. So we're swapping the position of the yellow and the pink pointer, and we'll increment both the pink and the yellow. But in the case, we only increment the yellow if the number is smaller. So if we get into this case here where the pointed number by the pink pointer is smaller than the pivot, we increment yellow. And if not, we just going to increment j, because this is a pink pointer. The pink pointer always gets incremented, and the yellow pointer only gets incremented as we find an element that is smaller than the pivot, because, as I said before, this is the counter of how many elements smaller than the pivot we found. So this is essentially what we're doing here. We're comparing at each iteration of the pink pointer if the pointed number is smaller than the pivot, and if so, we're going to swap the pink with the yellow, and we're going to increment the yellow by 1. So we found one more element that is smaller than the pivot, and we're going to increment j every time at the end of the loop. Once we reach the end, so we keep doing this. Once we reach the end, so once we break off the loop, meaning that the pink pointer has reached the same index as the pivot, the only thing we have to do is swap the yellow pointer with the pivot. So we swap the yellow pointer. So in the array, we have to swap the yellow pointer. Yellow pointer is I, and the pivot. That's all we have to do. That's all we have to do. And we have to return now, where is the new pivot, right? Because the pivot has been shifted from the last position to a position somewhere in the array. And this position is represented by I, because I points to the element or to the position that we have swapped before. So we have to return the index of the yellow pointer. That's where our pivot is now staying at. So this is essentially all we have to do in this partitioning function. we start the pink pointer, the yellow pointer, we do the loop comparison, we increment the pointers accordingly, and then at the end we swap the pivot with the yellow pointer and return the yellow pointer to represent the current pivot position. And we use this pivot position to call the quicksort function recursively on the left side and on the right side. And all we have to do here now is call or create our swap function, because we have not defined a swap function. So let's create here a void swap that receives an array, an integer x, an integer y, and we create an int temp that will be equal to the array of x, and array of x will be equal to array of y, and array of y will be equal to the temporary variable. And that's basically it. All you have to do now is the function declarations. So let's create the function declarations for these functions. So 5j, let's paste it here, and let's search here for partitioning. So this is the function declaration. Paste here, and last but not least, we have to search for the swap function. And that's it. That's all you have to do. So let's just check if we're printing accordingly. Yes, we are. So in the main function, we're going to print the unsorted arrays, or the original arrays. We're going to sort them using QuickSort, and then we're going to print the sorted arrays. That's all you have to do. So I guess we're good. Let's check if there are no problems. So no problems. Let's clear the screen, and let's compile it and run it. And there you have it. So this is how you implement QuickSort. It can be a kind of tricky if it's the first time you're implementing QuickSort. If not, you already have an understanding of how to do that, but it's easier if you always create some sort of board drawing, so you can actually understand how you're going to implement the algorithms, because the edge cases, it's easier to understand how you're going to treat the edge cases. For example, if you only have one element, or how it behaves with two elements, and so forth and so on. It's easier to treat those edge cases if you have a board that you can visualize what's going on during the algorithm execution. And once you understand what's going on, you can easily transfer it into code by grabbing the concepts from your board draw and put into actual code and execute it. So this is QuickSort. I will be bringing more videos about different sorting algorithms as well. I'll probably bring merge sort or something similar to merge sort on the next video. And if you have any questions, you can post on the comments down below. I hope you enjoyed this new format of video. I'll probably be bringing the next videos using the same format, using slides, because I guess it's more it's more easy to explain instead of going around with the mouse as I did in the previous videos. And yeah, thanks again for watching, and I'll see you on the next video. Peace.